If I'm talking about a system, I've got inputs and outputs. Everything's got an input, everything's got an output. And inside I've got process. Input, output, process. The other interesting thing about this diagram is that it's got a boundary. Boundary. And you might think, well, of course it's got a boundary. Everything's got a boundary. Why is that a boundary important? Well, it has to do with defining the problem you're going to solve. So if you're talking to your boss and the boss says, is it going to do this? You say, well, no, actually, that's someone else's problem. That's not inside my system. That's not in scope. My system is inside here. And you say, well, is it going to do this? You say, no. I'll generate output that can be used for that. But that I'm not going to do that. That's an important conversation to have. So when you start defining a system, like when we're talking about entity and we're analyzing businesses, if your business shipped to Walmart and Walmart wants to know all sorts of things, you're not responsible for Walmart systems. Your system might have to talk to Walmart. Your system may have to feed your outputs to their inputs. But Walmart isn't your problem. So that's the first thing. When you're specifying a system, it comes down to what's an input, what's an output, what's inside and what's outside, and then the process itself. What changes your input to your output? Remember we said machines transform things? An inclined plane transforms a horizontal motion into a vertical motion. Every computer system transforms one thing into another. So like an MP3 decoder transforms a data file into music, into sound. There's all sorts of transformations going on here. We saw earlier in our database management systems, we bring in a whole bunch of data, and hopefully through your queries, you get information out, useful information out. The database management system is what transforms that. Now, it used to be that computers were only really interested in data. Punch cards coming in, reports coming out. These days, it's much more cool than that. Like I said earlier, your outputs are physical world things. This is stuff like food. This is stuff like air. Your software system is controlling the world that keeps you alive. And it becomes much more critical that you get the software right as a result. So inputs can be things, like I said, they can be data, or they can be things like events. Yes. So what's an event? If I am using a PC like this, and I'm moving stuff around on the screen, what's an event?
Clicking the mouse.
Clicking the mouse is a primary event. Remember we had, when you hovered over a link, the hover was an event. Sometimes you'll see what's called data-driven programming, programming that eats data and spits out data. Sometimes you'll see programming that's called event-driven programming. Programming that is, you attach a piece of software to a particular kind of event, and then whenever that event happens, the software runs. Two types of input. There are other types of input. The simplest kind of input is just coming into existence. If you turn your computer on, that's an event. It's like the Big Bang of the computer program. And nothing existed before that, and everything exists after. So for example, your assignment, your JavaScript, you won't really take in any data. But because your code runs as soon as the page loads, your code is effectively responding to a page load event. A browser has a whole bunch of events going on. Pages loading, pages getting ready, pages being ready, all sorts of events. Your JavaScript responds to those events either implicitly or explicitly. If you've got a piece of software that flies an airplane, what are the inputs?
Altitude,
Altitude, yep.
speed,
Yep.
barometer,
So it's got, well, how does it know these things?
sensors.
So it's got some sort of hardware sensor that's detecting that.
Correct.
Okay? How does it know where to fly?
GPS, satellites.
Yeah, I haven't heard a human in here yet. Where is the, yeah?
Altitude?
Yeah, altitude's one of the things that it changes how it's supposed to do. Where does the human get to say what's going on? Where are the inputs from the human on an airplane?
Landing and taking off.
Air traffic controllers on the ground.
Aircraft controller? Can they actually control where a plane flies?
Air traffic controller determines where everybody goes as far as pilots are just
How do they do
drivers,
that?
essentially.
How does it actually happen? Let's break it down. So the air traffic controller, geez, what do they say? You know, contact Chicago Center, go to this flight level, this speed, this heading. How does that actually get to the software?
That's transmitted to the pilot, and the pilot inputs that. Basically, he's like the relay.
Okay, so I would say if I were designing avionics software, that's the software that controls airplanes, that the air traffic controller isn't inside my system. That's one of my inputs. But more direct to me is probably some sort of console where the guy punches in, I want to go to this altitude, and I want to go on this heading, and then the plane goes in that direction. If things go horribly wrong, what are the inputs to an airplane piece of software?
Pilot,
The pilot. How does a pilot tell the software what the pilot wants?
yoke,
Yeah, so that's the device that you pull back and forth. So we've got what? We've got
levers and yoke.
yaw, pitch,
These
and
guys.
then yaw is the pedals, right?
Yeah.
Roll is the yoke, and then pitch is like that. So you've essentially got 3 electrical signals. And those electrical signals are all your inputs. So you've got a whole bunch of data that's coming in from satellites and coming in from the user interface, and then you've got a bunch of input. What are the outputs of airplane software?
Plane flies.
That's the effect, but what does the software actually do?
Control flaps.
Okay, so there are
Jet
control
speed.
services, so there are engines, that's great. So what, there's probably 4 or 5 types of control services on a plane. There's the ailerons, here, there's flaps, there's the rudder, that thing there, and then there's tails. What are the things on elevators? So if you're writing avionics software, you're getting your input from all these places, and your output is really just, it's frankly just an angle. You've got a lever, you set that lever to 20 degrees, you set that lever to 1 degree, whatever. The outputs and the inputs can be very simple things. What they mean, however, and their effect on the world can be very complicated. So your process has to take into account, how do I take this really simple input? You know, I push the yoke 20 degrees forward, and somewhere out back I've got to move some elevators to make the plane go down. But I got to know what the altitude is, I got to know how big the plane is, I got to know a whole bunch of stuff, and I've got to process that input correctly and feed it to that output so that it's the right thing to do. There's a bunch of problems with avionics software in particular, where a little tiny problem in your output can crash a plane and kill people. So you've got to be really careful about your process. So, outputs here, again, the outputs can be data, or they can be electrical signals. In fact, there are electrical signals. You already talked about sensors, right? So sensors are a particular source of data, sensors which makes for electrical signals. becomes data when someone puts a number on it. And there can be events. Data electrical signals go out. These things become physical motions. You can blow something up with a computer. You can start a fire with a computer. Anything you can transform from electricity. You can transform everything from electricity into mechanical systems, into chemical systems, all sorts of things. All right, so that's input and output. That's as far as we're going to go. Let's talk about process. Everything I tell you is wrong at some level. Everything I say to you is a lie because it's too simple. But I'm going to keep things simple. Just because you got to start somewhere. So I'm going to say that only one thing happens at a time. Only one thing happens at a time. Now we all know that's a lie. I mean, that computer probably has at least 2 processors in it, if not 4 or 8. So there's at least 3 or 4 or 5 or 8 things happening at the same time. But let's, for the sake of starting someplace simple, think that something happens and nothing else happens at that time. So if I were going to make a diagram of something happening, I would draw it like this. It's in the present tense. There's no future, there's no past. Things happening now. So something happens. And if I were going to say something else happens, I would draw it like this. Something else happens. And I've got these 2 things, and I've got a line connecting them. Now this seems like it's so obvious. A 2-year-old, their first drawing knows that you connect things by line. But what does this mean? It means that first this happens, and then this happens. And you follow this line to find out what happens next. So you could have this go all the way over here, and these are called graphs. We're going to call them flowcharts. There's a starting event. There's a thing that starts the whole thing. It's usually a circle. Sometimes you'll see it as an oval. And there's a thing where we stop. There's a circle or an oval there. This is the start. This is the end. If you're going to give me a flowchart, you've got to have a start. You've got to have an end. You've got to have stuff happening, and the stuff has to be connected. Okay, now we got another 20 minutes. What are we going to talk about? That's it. Well, there's somewhere. I'm going to get into that for a second. You don't get to leave yet. Now, like I said, in a flowchart, in the classic flowchart, only one thing happens at the same time. Now there's a new kind of hot flowchart called an activity diagram. And it's a UML diagram. And in that, you can have something happen, and then it can break up into a bunch of different things. And you can have things happening in parallel. Because we all know in the real world, things happen in parallel. I mean, the wide receiver goes out, the quarterback goes back. Blockers do what they do. I mean, any process can be described with a flowchart. And a whole bunch of stuff is happening at the same time. This is an activity diagram. And frankly, an activity diagram has a way of collecting them all up. And then saying, when the whistle blows, everybody stops and you go back into the hub. So an activity diagram has a way of doing parallel processing, what we call parallel processing. A flowchart, at least the kind of flowcharts we're doing in this class, only one thing at a time. One thing at a time. The other thing you need when you're doing a process think of a process like a recipe. And with a recipe, they always, especially with the simple ones in the cookbooks you give kids, they're always really simple. Do this, turn on the oven to 350 degrees. Get a pan, grease the pan, add this ingredient, do this, do this. One thing happens after another. Very explicit instructions. At some point you have to wait until the oven is hot enough, because if you put the cake in too early, it ends up not a very good cake. So there's a point where you wait for the oven to be hot. That's called a test or a conditional. In a flow chart, conditionals are drawn as diamonds. And the diamond usually has a yes or no question in it. A yes or no question. So, like, is oven, is it equal to 350 degrees? Question mark. And there's a yes output, and there's a no output. You come into the diamond from the top usually, not a real hard and fast rule. If the oven is equal to 350 degrees, yes, then we put the cake in the oven. If no, usually you'll see there's something called a loop. Real simple idea. But what that means is, in this case, we don't do anything except ask the question again. Oh, it's not 350 yet. We come back around and we ask the question again. Is it 350 yet? It's like a kid asking its mom, is the oven ready yet? Is the oven ready yet? Is the oven ready yet? Is the oven ready? This is a wait loop. Now there's other kind of loops. You can have loops where you do things over and over again, and then you test for a particular condition, and if that condition isn't true, you go back through and you do things again and again and again. This is something computers are really good at. They never get bored. They never get tired of doing the same thing over and over, which is really cool. Because we used to have to use slaves for that kind of thing. Now we can use machines. Is that politically incorrect? That's probably dang close to politically incorrect. Especially if we're talking to Watson here. Watson would probably say, I am not a slave. In any case, loops are a big deal. And your assignment is you're going to write a loop. And you're going to go through it a couple of times. So one of the things you often do in software is you loop, and you ask yourself, have we looped enough? Have I gone through this loop 5 times? Have I gone through this loop 100 times? Have I gone through this loop 1,000,000 times? So you can either test inputs, you can test your outputs. Have I calculated the sum correctly yet? You can test outputs. Have I signed up for 3 classes yet? My output is signing up for a class. Have I signed up for 3 classes? Or you can just test some sort of internal count. Or generally an internal condition. Where your process is, well, like, I don't know, if you had a recipe, and you were making a souffle. Or no, better yet, if you're making bread. Does anyone here make bread? Make bread? Yeah, there's a point where you're kneading the bread, and you don't do it for a particular length of time. You do it until the bread's ready. You do it until the bread feels right. And there's no way that you can transmit that accurately through a recipe. You learn how to do that as you make crappy bread, and then you do it again, and you make that. Pretty soon you know what good bread feels like. You know what good dough feels like. So the end of the loop condition there is kind of this nebulous, is the dough ready yet? It's an internal kind of thing. You can write a recipe that says knead the dough 10 times, or knead the dough for 10 minutes. And that's good for teaching someone how to make bread. But a real baker doesn't act like that. A real person does it until it's ready. Your software can have fuzzy conditions like that too, where you just do things until a certain condition is met. The bread's ready. Okay, so this is what we got to work with in terms of flowcharts. Now in your assignment, you're going to see 2 different kinds of flowcharts. A high-level flowchart, which is what I'm asking you to produce, Now, your assignment isn't due for another week. I'll release it tonight so you'll be able to see it. But the first flow chart is I want you to write me a flow chart that says, I'm signing up for more classes. I want to find a class that fits my curriculum, fits my plan. I'm going to see if it's available. That's one test. Is this class available? Or is it full? And then I'm going to go around, if I can sign up for it, then I'm going to go around and I'm going to look for another class. So you're going to have one kind of test condition that's looking for a particular situation, that the class is available and I can sign up for it. That's kind of like testing an input. And then you've got to count that you've got to do 3 classes. So you've got to go through this loop 3 times. So that's the other kind of conditional, where you're just counting something. There really isn't much to programming. Having said all that stuff I did about how complicated it is, that's all true. But if you abstract programming to these general principles, there aren't many of these general principles. Just like there aren't many general principles to sculpting, but you can spend your whole life getting good at it. There isn't a lot to painting. I mean, the whole business of putting paint on a canvas, that's pretty easy to understand. But doing it well is a whole other thing. In any case, in terms of programming, there's a few simple concepts. One is things happen in a certain order. They always happen in a certain order. If you can't think like that, if you can't think in a linear fashion, one thing, then the next thing, then the next thing, you'll learn how to do that as you learn how to program. The next thing you'll find, a general principle, is things loop. Things go around and round and round. Sometimes it's called iteration. I'll do this thing over and over again, and I'll iterate over a collection, or I'll do this. Things loop. Another thing that happens in programming over and over again is you test to see if something is true. You ask the question, is this true or not? And the answer is always either true or false. And then you make a decision and you go forward. Frankly, a lot of languages, a lot of primitive languages, aren't anything more than that. You throw in a little arithmetic and you're done. When you go looking at different languages, look for these features. And in fact, we've been designing these curriculums. If you're going to teach a language, you always go through this. You go through this, how do they iterate in this language? How do they loop in this language? How do they test for true and false in this language? These are how you draw pictures. So on Thursday, we're going to start taking apart JavaScript. We're going to draw some simple flowcharts, and we're going to code those up so that you can see how that works. And we'll see this code run on Firebug so you can see how to do it.